Today, we welcome the Professor Naian Liu from the professor and a director of the State Key Laboratory at the USDC in China. He's very much wider area of the expert, including the wildland fire and fire dynamics and many of the things. And he's a fellow of the Combustion Institute in 2018. And he is the vice president of the Asia-Oceania Association for the Fire Science and Technology. And he's the board member of and the director of International Association for Fire Safety Science. And he has many prizes and honors, and I cannot counting and also introducing here. But this time he's gonna presenting the very interesting the wildland fire things. His title is Wildland Surface Fire Spread, Behavior and Mechanism Transformation. So let's welcome Professor Naian Liu.
Good morning. Thank you, Yuji, for your kind introduction. I'm honored to have a talk at this conference. During the past several years, there have been a large number of very serious wildfire accidents that occurred in the United States, in Australia, in Canada, in Brazil, in Europe, and China. And the increasingly very serious wildfires have been receiving more and more academic attention. When a surface fire occurs, it usually undergoes many changes, many very complex changes in behaviors and mechanisms under the different conditions of fuel, weather, and topography. And it will finally reach a state with very high burn intensity and the rate of fire spread. So my speech will focus on the mechanism, transformation, and the behavior transition that control the growth of surface fire. My talk will be given in three parts. First, I will discuss some fundamental complexities in surface fire spread. And then I will focus on the mechanism transformation and the behavior transition in surface fire. Finally, I will propose some challenges of future studies. As for the complexity of surface fire spread, the scaling law is a big problem. As we know in physics, the fire lines in surface fire are essentially buoyant diffusion flames. Due to the interaction of a combustion and the heat transfer and atmospheric flow, the fire lines of different scales may have varied mechanisms that caused completely different burning behaviors. For example, the classic experiments of Belinov and Kodyakov in the late 1950s, as shown in the left figure, indicated that the burning rates of diffusion flames non-linearly depend on the fuel size. They demonstrated that such a nonlinear variation essentially stems from the different dominant heat transfer mechanisms. In the right figure, we can see that for diffusion flames, the flame height depends on the heat release rate by a 2/5 power law. Similar nonlinear trend applies to flame radiation because we know the radiation depends on the flame size. Therefore, I enjoyed the words said by the Biran in 1950s. He said that a high-intensity erratic fire cannot be considered as a large-scale model of a low-intensity fire. The fire spread models are generally divided into three categories. The statistical models involve many statistical correlations from laboratory and field experiments or historical case studies. The semi-phase models are generally established based on a framework of energy conservation, just like the Rosmel model, with many empirical data and correlations to close the problem. And nowadays, the phase models try to describe the complex processes of fluid mechanics, combustion, and heat transfer in fire spread. For the phase models, it is generally assumed that the energy of the combustion is transferred, first released and then transferred from the flame to the unburned fuse ahead, increasing the temperature to the so-called ignition temperature by the combined effects of various fuel preheating mechanisms. For the radiation, it may include the flame radiation, the amber radiation, and the radiation loss you can see here. And for the convection, it includes the surface convection, interior convection, the convection due to the turbulence diffusion, that is a very short distance convection, and also the convective cooling. But the key point is that varied viewpoints exist on the fuel preheating mechanisms. For example, this table lists some major one-dimensional fire spread models by different authors. As you can see that different authors considered very different major preheating mechanisms, mainly surrounding the relative importance of radiative and the convective heat transfer mechanisms. We take the convection as an example. In the 1970s, Rosemel ever indicated that when there is no wind, the convective cooling due to the indraft of the air should be considered. However, he did not describe the convection ahead of the flame front for upslope fires. For such fires, our experiments revealed that the convective cooling undergoes a physical transition with increasing slopes. When the slope is very low, the convection is dominated by the natural convection. However, when the slope reaches a certain value, the convection is dominated by the combination of natural convection and the flame-induced convection. So that is essentially a kind of mixed convection. When we integrate these findings into the model, as shown in the right figure, we can see that the prediction agrees well with the experimental data for very high slopes. Another complexity of surface fire is concerned with the uncertainty in physical models. The model errors may arise from unreasonable assumptions, rough approximations, or inaccurate measurements for formulating the models. As we know, it is generally assumed that the fire spread is in the steady state with fixed flame properties, including the flame shape, length, tilt angle, emissivity, and also flame temperature, and fixed fuel bed properties, including the fuel density, fuel moisture content, and the packing ratio of the fuel bed. And also we assume constant wind speed and the terrain slope, as well as the assumed values of ignition temperature. As shown in this figure, different authors have very different estimations of the model parameters. For example, this slide shows an uncertainty analysis of the model parameters. For example, we can see that flame temperature is usually introduced in the model as a constant parameter, but different authors have varied flame temperature values within 9 to 1100 Kelvin degrees. And the uncertainty analysis shows that the prediction is very sensitive and highly depend on the assumed values of flame temperature. And also the estimations, different estimations of the parameters, including the fuel consumption efficiency, ignition temperature, the flame length, and heat convection coefficients, all have very remarkable influence on the prediction results. Another complexity is concerned with the physical modeling of fire line. As we know that in the fire spread model, the fire line in the surface fire is usually assumed as a linear or rectangular turbulent diffusion flame. However, we know that past studies mainly address the pool fire, the diffusion flames of circular fuel sources. And during the past several decades, very few studies have touched on the rectangular diffusion flame. Some very limited and available studies have indicated that, different from the circular fuel sources, for the rectangular diffusion flame, the flame length, flame height depends on the heat release rate, first by a two-step power law. And when the heat release rate reaches a certain value, the power will change to 2/5. The above discussions address the major mechanisms, major complexities in mechanisms of the fire spread itself. However, maybe a more important point is that a surface fire spread may undergo many kinds of very complicated behavioral transitions under different conditions. This is a campfire in 2018. It has a peak rate of spread up to 33 kilometers per hour. We know that any surface fire in its initial stage is very weak in burn intensity, and the spread rate is on the order of only 0.1 kilometers per hour. However, many cases indicated that in large wildfires, the peak rate of fire spread normally fall into the range of 10 to 30 kilometers per hour. So you can see that this is a several hundred-fold difference. During this process, many kinds of intensely burning behaviors act as the forcings, act as the driving forces to induce the fire spread accelerations. Such behaviors associated with surface fire spread include some large-sized flames, such as the conflagration, firestorm, and a fire whirl, and also the unique spread modes, including the crown fire, spore fire, and the eruptive fire. These extreme fire behaviors with very high burning intensity and a very fast spread rate, they are essential factors to make the original very mild fire spread to undergo a non-steady transition and finally reach a new steady state with high levels of burning rates, burning intensity, and spread rates. Now let's see the major mechanism transformation and behavior transition in more detail. We discuss this topic in three aspects. First, I will discuss the fire lines merging, because many cases indicated that the merging of multiple fire lines is an essential mechanism for inducing the above-cited extreme fire behaviors. And then I will discuss the topography effect with a focus on the flame attachment and eruptive fire under different topography configurations. And finally, I will discuss the wind effect on the fire spread mechanisms. This slide shows that the fire lines merging can be observed in experiments and also in many natural fires. For example, you can see that the two fire lines here, they merge to induce very fast burning. And also you can observe here, it induces a fire whirl. And the experiments of Silvani indicated that the merging of the two flame fronts, they induced a very significant increase of the burning intensity and the spread rate. That is the laboratory experiments. In nature, besides the spreading fire lines, the multiple fire lines could be induced by lightning, by flame radiation to induce many fire points, and also by the spotting fire. All these multiple fire lines, they have very significant interactions among each other. For example, in the Canberra fire in 2003, you can see that the merging of two large, very large-scale fire fronts, they merge to induce very fast fire spread. However, unfortunately, until today, very limited studies have investigated the interaction of spreading fire lines. More than ever used the FireStar and WFDS to simulate the interaction of the head fire and the backfire, showing that there will be a significant increase of the heat release rate by the interaction of the two fires. That is attributable to the increased radiative heat transfer between the fire and the fresh fuel. In particular, they indicated that the in-draft flow induced by the head fire would draw the backfire, you can see here, towards the unburned fuel, separating the fires. And then they will induce the increase of the heat transfer between the backfire and the fuel, promoting the rapid spread of the backfire. Especially when the wind speed varies high, the simulation results indicated that almost all the models, including the WFDS, FARTEC, Behave Plus, and the MK5, all predict the rate of fire spread. This suggests that further studies of fire alarms interaction should be conducted to achieve more understanding, more deep understanding on the interaction mechanisms, mainly surrounding the competition of the heat feedback and air entrainment, especially for the multiple rectangular diffusion flames. Second, the topography-driven behavior transition. Typical topography configurations include the upslope fire and the canyon terrain. So in upslope fires, the flame attachment plays an essential role to induce the fire spread acceleration related to eruptive fires. And in canyon fires, this is the experiments of our group, you can see that very complicated evolution of the fire lines could be observed. And also firework could be also induced in upslope fire or other different conditions of wind and topography. The eruptive fire, we can regard it as a kind of a very special surface fire spread because of its very marked spread rate. In literature, there are many names appearing to describe this phenomenon, such as the blow-up, flashover, and the fire eruption. Although there have been many eruptive fire accidents reported, we still know little about the mechanism behind this phenomenon. Nevertheless, we can see that many mechanisms have been proposed in the literature, such as the atmospheric instability theory, the thermal belt theory, gas accumulation theory, flow attachment theory, and the self-acceleration of spread. However, unfortunately, most of these theories remain at the level of conjecture with no experimental verifications. So we touch on the two of them. First, the gas accumulation theory. It is associated with the canyon terrain. It is assumed that in the canyon terrain, the unburnt flammable gaseous products can accumulate in the deep canyon. They can be generated by pyrolysis of vegetation or the volatile organic compounds. Then the unburnt flammable gases may be mixed with air and then ignited to produce very significant premix flame, not diffusion flame, and also even deflagration that will induce very fast spread. This is a very reasonable explanation of the so rapid fire spread. However, unfortunately, there is no experimental verification on this theory. Another one is a flow attachment theory that is related to upslope terrain, just like the experiment of Dalt using the field bed to observe the fire spread acceleration. Normally, it assumes that when the slope is very low, then the flow around the flame will toward the flame. That is a kind of convective cooling over the fuel surface. However, when the slope is very high, so the flame flow will attach the fuel surface to induce very significant convective heating. So this sudden change is believed to be the essential mechanism for fire spread acceleration in absolute terrain. This theory is supported by some experiments. For example, our experiments showed that when the slope reaches a certain value, the rate of fire spread underwent a sharp increase. And the velocity and the heat flux data all demonstrated that the sudden change from the convective heating to convective cooling to convective heating should be the essential mechanism to induce the eruptive fires in absolute fires, absolute terrain. Then for the canyon terrain, experiments of my group collaborated with Professor Dominguez Vigas. Here you can see it's very interesting. It shows very complicated evolution of the fire lines. First, when the canyon slope is 0, alpha denotes the canyon slope, major slope. So you can see that the fire line is just like a very normal linear flame front. However, when the slope reaches 20 degrees, so the fire lines looks like a butterfly. It's very strange. And when 30 degrees, you can see that the fire lines became to be separate and in parallel directions. And the velocity and the heat flux data all demonstrated that for the last one, when the slope is very high, the two fire lines will have a very significant interaction to each other and then to induce very significant convective heating ahead of the flame front. So that is believed to be the essential mechanism for inducing the eruptive fires in such kind of topography configuration. However, there is no physical models to predict the evolution of the fire lines. So that is a challenging topic. We should try to use much efforts to realize the accurate prediction of the fire lines, the complicated fire lines in canyon terrain. It should be noted that fireworks could also be induced in the fire line in surface fire. This is a firework in Brazil in 2010. You can see that is a moving firework along a fire line. We simulated these phenomenon in laboratory and found that the wind is a necessary condition, that the wind should attack the fire to induce the firework. So the problems to be elucidated include the formation condition and the mechanism of such fireworks, the critical wind speed and the occurrence frequency, and also the mechanism of flame moving of such fireworks. Our results revealed that the essential conditions for such fireworks include a reasonable attack angle of the wind toward the fire, and also the wind speed within the critical range. And in the bottom image, you can see that the occurrence frequency of such fireworks first increases and then decreases with the increasing wind speed. That is caused by the competition of the two velocity vectors. The first is the parallel velocity vector that is along the fire line, and that this kind of vector plays a positive role. However, another is a perpendicular vector that plays a negative role. By this analysis, we deduced a scaling law that characterized the critical wind speed of such fireworks with the heat release rate and the attack angle. And the physical analysis have coupled the formation mechanism with the line fire plume and the horizontal vortex line. And in experiments, we can observe the flame moving downwind and upwind. And analysis showed that the downwind firework is essentially controlled by the drag force, lift force, and the ground friction. However, the upwind firework is induced by the flow separation. So different mechanisms. Now we move on to see the wind-driven fire spread. Wind can change the fuel preheating mechanisms ahead of the flame front. Wind is also essential for the firebrand's transport in spotting fires. So as for the wildfire triangle, wind as a major weather factor, many cases indicated that the wind plays an essential role in many dramatic wildfires. Wind will induce the flame tilting naturally. That will induce the increase of the radiative heat transfer. However, it will also induce flame pulsating with the interaction with the buoyancy that will induce the significant increase of convective heating. Therefore, the surface fire in wind may undergo very significant changes in the burning behavior and the preheating mechanisms. However, the currently used fire modeling systems, such as the Behave Plus and also Farsight, they still rely on very old statistical or very early semi-physical models, just like the Rosemel model, for operation purposes. And such models are inadequate for predicting wind-driven fire spread because of the lack of the fundamental understanding of the fuel preheating mechanisms and also the behavior transitions. And in later 1980 to 1990s, some authors consider that the wind affects the fire spread mainly by changing the radiative heat transfer process. For example, Albany in 1985, he considered that the flame sheet acts as an effective barrier against the wind. In that condition, it means that the wind cannot pass through the flame, and so the flame radiation plays a dominant role. In Baines in 1990, he considered that the flame tilting makes the plume closer to the fuel in a highly intermittent manner. So the intermittent manner will enhance the convective heating. So all these models, they assume that the flame front is a static plane with fixed length and angle of the flame. Later, some models consider that the convective heating, especially under very strong wind, should be very important. For example, Morandini, so they first simulated the fire spread under the wind, but they did not consider the convective heating. They found that under the highest wind speed, so the prediction underpredicted the experimental data significantly. Then they used the convective heating model by Albert Simeoni, and they found a very good agreement with the experimental data. And some models, they have tried to develop some physical models. Physical models means we have to simulate all the sub-processes in fire spread. And Porty, for example, he conducted a two-dimensional multi-phase simulation by incorporating the turbulence, radiative heat transfer, soot formation, and others. And the simulation results identified the flow transition from buoyancy to wind-dominated regime with increasing wind speed. But as you can see that such models so overestimated the flame attachment to the fuel bed. And the simulation especially indicated that under strong wind, the wind can pass through the flame front, so that the convective heat transfer may play a more important role. For example, you can see when the wind is weak, so the flame front just like a barrier to prevent the passing through of the wind. So the radiation of the flame plays a dominant role. However, under strong wind, you can see that the wind can pass through the flame front. And but there is no but in this study, they did not provide any experimental verification. So Marfini provided experimental interpretation of the convection mechanism. Previous models generally assume a homogeneous field bed, but real fields are usually discrete. Especially the measurements by Marfini, they indicated that the radiation is insufficient alone to ignite and support the phi spread of fine-sized particles. They demonstrated that under the strong wind, the wind can pass through the flame front and interacts with the buoyancy to form a peak and a trough structure. That is a very special structure. The structure is characterized by the counter-rotating Taylor-Gardner vortex, and such a structure, the downdrafts from the longitudinal rolls force the flame down and forward into the field bed. Therefore, the convective heating is significantly enhanced. Recently, Fraggi, he provided a very good simulation to reproduce the 3D peak and the trough structure using physics models of RAMS and LES. You can see that the simulation results showed that the vortex pairs can pass through the flame front. So this is the velocity data, this is the temperature data. They all demonstrated this point. You can see that the vortex pairs pass through the flame, then induce the convective heating effects. The wavelength of such structure was obtained by the FFT of the temperature above the fire line. Thereby, we can define the Behrend convection number and also Froude number. Behrend convection number denotes the ratio between the buoyancy power and wind power inertial force, and the Froude number denotes the ratio between the wind inertial force and buoyancy. So the analysis shows that the two numbers can be correlated by a 2/3 power law. That suggests, that implies that the peak and the trough structure has some similarity in different scales. However, for such scale, the mechanisms behind it is still not well understood. In summary, we can summarize the wind effect on fire spread mechanisms. We can see that so many very complicated behavioral transitions, they induce transformations of flow and heat transfer mechanisms. For example, when there is no wind, the flow is 2D with radiation dominated. However, when with wind, especially very strong wind, so the flame flow will become to be 3D non-steady flow dominated by both the convection and the radiation. And we can see that the flame inclination will change the view factor for the radiation. Flame attachment will induce the flame content to induce very significant turbulent diffusion and the convective heating. And the flame pulsation will produce the flame vortex that will significantly increase the convective heating. So all these effects will influence the rate of fire spread. So more fundamental understanding of such mechanisms and behavioral transitions will help us to enhance the predictive abilities of operational models and the tools. We now discuss the spot fire problem in brief. Spot fire consists of 3 sequential processes, that is the firebrand generation, firebrand lofting and transport, and the fuel ignition by attacks of the firebrands. It is not very easy to study the firebrand generation in surface fires. Some authors conducted the tests of prescribed fires together and to characterize the firebrands by measuring the firebrand mass, shape, projected area, energy properties, firebrand flux, and so on. And the results show that the firebrand generation depends on various factors such as the size and types of the fuels, the fire intensity, and the local gas velocity. Especially there has been very little work to understand the thermomechanical mechanism in the fuel breakage in firebrand generation. Some models try to couple the breakage model with the thermal decomposition model. By such coupling of the models, they try to identify the breakage regimes by the effect of the combustion. And various factors have been considered, such as the size and the type of fuels, local gas velocity. However, the major challenge is how to couple these behaviors with extreme fire behaviors, such as the fire war, firestorm, and the conflagration. And for the firebrand lofting and the transport, the focus is to predict the maximum spotting distance. Many kinds of flowing fields were considered, including the burning trees, live thermals, wind-driven surface fires, and so on. And the model simulation has considered the spot of transport of the firebrand of different shapes in turbulent boundary layer. However, it is challenging to model the combustion-induced decay of firebrand in forced convection. And for the firebrand ignition, so the hot particle-induced ignition is very typical by considering many kinds of firebrand characteristics. And the prediction is trying to reveal the critical particle size and initial temperature for ignition of different fuels. But we try to accurately quantify the effects of firebrand, fuels, and ambient atmosphere. And for the role of spot fire and surface fire, this simulation shows that the firebrand ignition significantly increased the rate of fire spread. Now, my talk comes to a closing by proposing some challenges. The first one is the theoretical elucidation of nonlinear behaviors in surface fires. We can see that different intensely burning behaviors are controlled by various mechanisms depending on the fuel, meteorology, and the topographic conditions. And during the surface fire spread, usually many kinds of mechanisms take effect, but usually only several major mechanisms play a key roles. So the challenge is trying to realize the accurate modeling of the behaviors to elucidate the significant interactions among fluid flow, heat transfer, and combustion. The second one is the critical conditions for the generation of different behaviors. So we try to understand the non-static transition to a new steady state with changes in controlling mechanisms and burning behaviors. And the challenge is trying to extract the critical condition and develop models to make connections between different behaviors. And the third is approaches to surface fire modeling of different scales, especially for large-scale fires. Currently, some efforts have considered the problem of large-scale simulation. For example, when the energy is very strong, it's strong enough to induce the atmospheric dynamics so as to affect the surrounding wind speed around the flame. So we should couple the atmospheric model with the fire spread model. Some efforts just like FireTech, but they use the very empirical models. So the challenge is try to realize more accurate predictions of the two directions of the interactions. So that's all for my talk. My thanks goes to Dr. Koyo Sato, who worked with us for over 10 years, and also many collaborations with Professor Dominguez Vigas and Dr. John Deris and Yi Wang from FM Global, and also Professor Albert Simeoni from WPI, and also many very useful discussions with Sarah, Marfini, and also Kozo Saito, and Professor Oleg, and Arno Trovi, and also Alexander Smith. Thank you very much for your attention.